Hello everyone. This is Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see the tutorial question bank discussion for the module 2. So, in the previous session, we have seen the tutorial question bank for the module 1. So, we have seen basically how do we derive the continuity equation using the fluid element approach. So now we will actually see the governing equation derived from the control volume approach, and we will use them for discretizing, and we will use the classification of PDE actually. So let us see what is the question. So build the mathematical and physical nature of flows governed by elliptic equations with an illustration of incompressible flow. So explain Neumann and Dirichlet boundary conditions. Okay. So first, basically whatever the governing equations we have. So we have the continuity equation, which is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So which is coming for incompressible flow. So if you see the compressible flow, so the equation is dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. So this is for incompressible flow. Okay. And this one is for compressible flow. Okay, here you can see the difference. So what we have, so when the density rho is constant, so what happens actually, so the term, so when the rho is constant, the time derivative term, so this will vanish here, so it will not be present. And so whatever the density terms which are present in the space derivative terms, so it will come out and it will be taken as common. And you can see, so this equations 1 and 2, so let's take this as 1 and let's take this as 2. So basically they are 3D. Okay, so if you want 2D, so dou u by dou x plus dou v by dou y will be equal to 0. So this term will vanish. The third term, dou w by dou z term will vanish. Okay, so this is what we have the continuity equation. Now, so coming to the mathematical and physical nature of the flows governed by elliptic equation. So basically the equations which are coming under elliptic are like diffusion terms. So we have actually seen in the previous sessions, so in this form, so a of dou square u by, let's say, dou x square plus b of dou square u by dou x dou y plus c into dou square u by dou y square is equal to, let's take some capital H. Okay, so here this is a general second order PDE equation. So for this we have seen the discriminant form, which is b square minus 4 into a into c. So which is, if it is less than 0, this is elliptic. Okay, so if b square minus 4ac is equal to 0, then it is parabolic. So if the same b square minus 4ac is greater than 0, that is hyperbolic. Okay, this is what we have. Now in the momentum equation, so we have, so basically dou by dou t of rho u plus, so I am writing 2D. Okay, I am writing 2D equation. So dou by dou x of rho u into u, let's say, plus dou by dou y of rho u into v is equal to minus dou by dou x of rho p, pressure, now plus mu square into, let's say, dou square u by dou x square plus dou square u by dou y square plus rho g. Okay, let's say this is body force term. Okay, this is body force term. So this one is the pressure term. Okay, so this is called the diffusion term. So which is coming because of viscous effects. Okay, so here you can see the left hand side is coming because of m into a. So mass is nothing but density into volume, which is rho into v. So a is nothing but acceleration, which is capital du by dt. Okay, so this is what we have. So this is so basically this is called capital D by d du by dt is substantial derivative. So which is, so capital du by dt is equal to the local derivative, which is dou by dou t, plus we have convective derivative, which is v dot del into u. Okay, so you can take v as a vector, which is u of I cap plus smaller u of j cap plus w of k cap. So the gradient will be dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. Okay, so when you do v dot del, so what happens actually? So you have u into dou by dou x plus v into dou by dou y plus w into dou by dou z. Okay, so this is what we have. So in this way, so you have this this is called convective derivative, this is called the local derivative. Now if you see this equation, so what do we have? So we need to see the elliptic equations. So if you observe the RHS term and the LHS term, so the diffusion term is coming under elliptic form. So you have dou square u by dou x square plus dou square u by dou y square. So why it is coming, we will see. Okay, so if you take the diffusion term, so what happens? Dou square u by dou x square plus dou square u by dou y square is equal to 0. So let us let us take as equation 3. Okay, again let us write equation 1 again here again. So dou square u by a into dou square u by dou x square plus b into dou square u by dou x dou y plus c into dou square u by dou y square is equal to 0. So let us take this as 4 or 1. Compare 1 and 3. So what happens? A is equal to 1, b is equal to 0, c is equal to 1. Okay, so this is what we have. Now when you do the discriminant d, so what happens actually? B square minus 4 into a into c. So b is 0 minus 4 into 1 into 1. So d is minus 4. So d has become less than 0. So with this what we have seen, so the diffusion term in the momentum equation is coming under the elliptic equation. Why? Because so the meaning of diffusion is spreading the fluid flow phenomena throughout or the entire domain actually. So example, let's say you have taken one agarbatti, so you had lit that one, or you have lit the candle or agarbatti one. So what happens actually? So when you lit that, so the smoke will diffuse throughout the room or throughout the domain. So the diffusion is coming because of the spreading phenomena, which is due to the viscous nature. Okay, so if the smoke is limited to certain region, so then it is not coming under elliptic form. So it is coming either in parabolic and hyperbolic form. So when the smoke diffuses with low speed and it spreads throughout the domain, so it comes under the elliptic equations actually. Okay, so from this, so we see that the momentum equation, in the momentum equation, the diffusion part is coming under the elliptic equations. So now we will see, so this part is done. Okay, so the elliptic equation with the set of incompressible flow we have seen. So now, so the Neumann conditions, so we will see, and Dirichlet boundary conditions we will see. So basically, what is the Neumann condition and what is the Dirichlet boundary condition, we'll see. So let us see what is boundary condition. So let us consider a control volume, so which has 4 boundaries. So this is called BC1, and this is BC2, and this is BC3, and this is BC4. So boundary 1, boundary 2, boundary 3, boundary 4. So in order to simulate, let's say, flow over a flat plate, okay, or flow, let's say, through pipe, okay, flow over flat plate, flow through pipe, in a realistic manner for in numerical simulations, what we do is like, so we create a geometry, or let's say we create a domain. For that domain, so we will give a realistic flow conditions, boundary condition, such that the flow propagates from the left hand side and will pass through the right hand side. Let's say this is LHS and this is RHS. Let us take this. Okay, flow enters and flow leaves. Okay, so pressure at LHS, P at LHS, and P at RHS, let's say. So pressure at LHS should be greater than pressure at RHS. Why? Because the flow propagates from one region to other region because of pressure difference. Okay, so let us take this point. So point 1 and 2. So P1, so this is along x-axis. So dou P by dou X between 1 and 2. So what happens? P2 minus P1. So this should be less than 0. Okay, the pressure gradient should be less than 0, such that the flow propagates from 1 to 2. So if we have greater than 0, so what happens actually? So if P2 minus P1 is greater than 0, what happens? The flow will have reverse effects, which is going from RHS to LHS. Okay, so whatever the situation it may be, let's say except for the heat transfer case, so in general the fluid flow will take place from one region to other region because of change in pressure gradient, so which is from high to low. So pressure will the flow will go from high pressure to low pressure. The flow will propagate. Okay, now in order to simulate these conditions, so what we'll give? So we will give the values on the at the boundary. So at LHS, you will give the value of pressure. Let's say P. LHS is 1 atmosphere. Okay, 1 atmosphere is nothing but 101,325, let's say, Newton per meter square. Okay, or you can take it as Pascal. So this value you will give. So at RHS, what you will give? You will give less than this. Let us take PRHS as 0. So let us take it as a vacuum. Okay, so what happens actually? So when you assign the values, okay, when you assign the values directly to the boundaries, so then that sort of condition is called the Dirichlet boundary condition. Okay, so what we have actually, so we gave the values. So P1. Similarly, we will give velocity value also. So let us you consider it as 0.1 meter per second at LHS. So there is no flow velocity LRHS. So initially we'll give B as 0. Okay. So you take BC2 as wall. For the wall, so what do we have is, so U at y is equal to 0 is 0. Okay. And dou U by dou y is not equal to 0 at what? So this gradient is changes. If it is equal to 0, what happens? So all the points you have same velocities. Okay. So you have the boundary layer which is dou u by dou y. So which is if it is equal to 0, what happens actually? Velocity at this point is same. This point is same. At every point you have same. So this is the case for the inviscid flow. So when you have the flow as viscous, so what happens actually? So your gradient, so dou e by dou y term will not be equal to 0. So with this, with this example, we can see that. So when I say Dirichlet boundary condition, so I'll give directly the values. So example is, so P is equal to 1 atmosphere. Let's say velocity is equal to 0.1 meter per second. So this is the case. Okay, and so U at wall is equal to 0, okay, meter per second. So this is one sort of the Dirichlet boundary condition. So when you want the Neumann boundary condition, so let's say, so dou u by dou y is not equal to 0. So this is one sort of Neumann boundary condition. Okay. So we take another example. So let's say one dimensional heat conduction of a rod. Okay. So let us take this as station A and this as B. Okay. So this length is L. So this is x-axis, this is y-axis. Okay. Okay. At x is equal to 0, T at A, let us take it as 500 Kelvin. Now T at B, we take it as 200 Kelvin. Let's say. Okay. So we have these aspects. So this is one sort of Dirichlet boundary condition. So let's say when you insulate here, top. Insulate top in the sense what happens here. So dou T by dou L along the length is 0. Okay, on the surface tops. Okay. So if you keep insulation, so at each and every point of the length on the top surface here, so you have the temperature variation. There is no change of the temperature variation along the length over the circumference. So what happens? This is set of insulation. So this is one condition which is Neumann condition. Okay. So with this we have seen basically what is the behavior of the elliptical nature. So we have seen the elliptical nature condition for the momentum equation where we have taken the diffusion term, and similarly so we have explained the Neumann condition and we have explained the Dirichlet condition using a certain flow or flat plate, and we have seen the heat conduction equation over the 1D element. Okay, so in the next session we will see basically the tutorial problems, and we will see the question bank questions for the module 3, and those are coming under these categories. So in the first we have seen the derivation of the continuity, momentum and an energy equation, and in the second part we have seen how do we classify those equations into elliptic and parabolic and hyperbolic nature, and what are those boundary conditions we have seen. And in the next third module we will see so how to discretize those equations actually. So those sort of numerical and tutorial questions will be discussed in the further modules. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.